Okay, this was lecture 1 in chapter 3, and I will call it also lecture 2. Is the continue. Okay, so this is about harmonically excited vibration. Okay, and the first thing we started with was the force harmonic excitation, in which you can see from the free body diagram, there is a force applied F equal to F naught sin omega t, which is harmonic. And using Newton's second law, we get the second order ordinary differential equation, but it is non-homogeneous. So there are two solutions, which is the total solution is homogeneous or complementary solution, and a particular solution. So that will be the total. And I called it XH plus XP. Now X8 is depends on the value of zeta, and there are four possibilities: either zeta equal to 0, which is undamped, or zeta less than 1, which is underdamped, or zeta equal to 1, critically damped, or zeta greater than 1, which is overdamped. And the solution, of course, is done in chapter 2, but we don't proceed with finding the constant. We don't apply the initial conditions on the homogeneous solution here, only on the total solution. The particular solution is to be assumed. There is no other way. We cannot derive a solution for the particular. How do we assume? We assume something or a function that is in the same form of the right-hand side. The right-hand side is sine omega t. If you look at the differential equation, it is F naught sine omega t on the right-hand side. Okay. So the Okay, so there was a problem with the internet and was disconnected. Okay, let me make sharing first. Okay, so we were talking about the particular solution is to be assumed according to the right-hand side of the differential equation. So the right-hand side contains sine omega t. Then we assume xp to be also sine omega t. We added the phase, so it might be 0 or it might be not 0, and that is can be determined in the solution. Okay, we will see what is the phase depend on. Okay, and so xp is the amplitude, which is here called capital X sine omega t minus phi. There are two unknowns here in the particular solution, x and phi. So we need to that the particular solution has to satisfy the right-hand side and the left-hand side. Okay, so xp satisfies when substituted in the differential equation. Okay, when we substitute in the differential equation, we should satisfies the left-hand side and the right-hand side. Yeah, they should be equal. Okay, that is the characteristics of the particular solution. The homogeneous solution will, when substituted in the differential equation, will equal to 0. But here, the right-hand side should equal to the to the left-hand side. Okay, so you can do this, but this is mathematically requires few steps, and that might be long a little bit here. So we can think of this differential equation in a different way. Okay, and that each term in the differential equation is representing a force. So we have mx double dot is a force. It's called inertia force. And cx dot is the damper force. Okay, and kx is the spring force. And of course, if not sine omega t is the applied force. So those forces contains inertia force contains the acceleration, damper force is the velocity, and the spring force is the displacement. And we know that those are vectors, and they are, you know, if you put a vector representation of displacement, velocity, and acceleration, we talked about this in chapter 1, that velocity is leading displacement by 90 degrees, and acceleration is leading velocity by 90 degrees and leading x by 180 degrees. So if you represent those vectors, okay, this is vector x dot, then perpendicular, I mean, this is x, perpendicular to this one is x dot. So here is 90 degrees, and out of phase, which is 180 degrees, is the acceleration. And the forces are, the spring force is along this. This is k times x, and this will be c times x dot, and this will be m times x double dot. So those are the direction of force vector. So we can add them. When we add them, the one that closes the polygon will be the right-hand side, which is the force. So as the magnitude, okay, you put the magnitude here. Okay, because x is xp, this is xp, is x sine omega t minus phi. So magnitude of xp, which is the amplitude, is x. Then amplitude of x p dot is what? Is x omega. And the amplitude for x double dot is x omega squared.
X double dot.
Yeah, x double dot. Okay, so along x is the spring force. This is the amplitude, kx. And perpendicular to it is the damper force, which is c times the amplitude of the x dot, which is c times omega x. And the inertia force, the amplitude will be m times omega square x. So this is the left-hand side. This is the left-hand side of the differential equation. The one that closes the polygon is the right-hand side, which is the magnitude of the right-hand side, which is the force, is F naught. Okay, so that will closes the polygon, and then you have this is representing the differential equation. So we use our knowledge of the terms that those are forces. Then we can find the constants of the particular solution. Okay, the phase in the particular solution phi means the phase of the displacement with respect to the exciting force. Okay, so this is measured with respect to f of t or f naught. Okay, now with this polygon we can draw a right angle triangle. I just project a line here. Okay, this is 90 degrees. Then you have a right angle triangle, and from which you can find some of the, you can find all the angles. Okay, so from the triangle, the right angle triangle, we have the hypotenuse is f naught square equal to the adjacent side, which is kx minus m omega square x. So it will be kx squared plus m omega x squared. And you can take x squared common. So this will be k squared sorry, here it is kx minus m omega squared. Minus m omega square x all squared. This is the adjacent side. The opposite side is c omega x squared. So you can take, as you can see, all the terms, they have x squared, so you can take x squared common. So this becomes k minus m omega squared all squared plus c omega all squared multiplied by x squared. So you can put x squared on one side and then take the square root. Okay, this becomes f naught divided by square of the square, but if not square becomes f naught divided by k minus m omega square all square plus c omega square. So this is x, which is the amplitude of the particular solution is found. It is found function of the system parameters, which is f naught is given, k, m, omega, c, all are given. And from here we can find the amplitude. To find the phase, you use the same right angle triangle, and you use tan of phi should equal to the opposite over the adjacent. Okay, so tan phi, the opposite is c omega x divided by the adjacent, which is kx minus m omega square x, and x will cancel out. So this becomes c omega over k minus m omega squared. Okay, so those are written here. X equal to F naught over K minus M omega square, all square, plus C omega square under square root. And phi is the tan inverse of C omega over K minus M omega square. Up to here, you find the solution because the particular solution is now known, which is function of the parameters. To get the total solution, you substitute and you use the initial conditions to find the constant. We will do one example regarding that. But X can be put in dimensionless form as well as phi. We can put this in those two equations using dimensionless parameters because you need to study the effect of all those parameters on the amplitude of vibration of the particular solution and as well as on the phase. So changing one of them, changing K, for example, or might overlap with something like omega n and zeta. So it's better to keep this in terms of omega n and zeta rather than on the original parameters, K, M, omega, and C, and F naught. So what we can do is we can multiply or divide by F naught, by K, divide the denominator by K and by numerator and the denominator by K. Okay, the same thing we can do here. We divide by K and divide the denominator by K. Okay, so when you divide by K, in the square root, it's going to become K squared because we are dividing from outside. Then inside the square root, you are dividing by K squared. Okay, so this will be a square root of all this divided by K squared. Okay, then we can divide K divided by K is 1 and minus M over K omega squared because the whole thing is squared, so you can take this and the whole thing is squared. And the same thing here, divided by K and the whole thing is squared. Okay, so we will have K over K, which is 1, then minus M over K, you divide by K here, and multiply by omega squared all squared plus C over K all squared. So M over K is the reciprocal of omega n squared. Okay, omega n squared is K over M. But here we have M over K. So this is the reciprocal of omega n squared. So this becomes omega over omega n squared. Okay, inside. So instead of this, and this will be K over K, which is 1. And C omega over K, we will see how we can do that. So we know that omega n is square root of K over M. Cc is 2m omega n, which is the critical damping coefficient, and zeta is C over Cc, damping factor or ratio. And we have in the equation of X, C omega over K after we divide by K. So we multiply by C and divide by C. So as you can see here, we multiplied by Cc, and divided by Cc. C over Cc is zeta. And you substitute for zeta with its definition, which is 2m omega n. you will reduce that C omega over K to 2 zeta omega over omega n. Okay, we can divide, this is F naught over K. F naught is Newton, K is a Newton per meter, so the unit here is meter for F naught over K is the unit of length. So you can get amplitude ratio when you divide by F naught over K. Okay, so on the left hand side, we divided by F naught over K and we get xk over F naught. And this is the amplitude ratio now. Okay, and on the right hand side, we have 1 over square root of 1 minus omega over omega n squared, all squared plus 2 zeta omega over omega n squared. Now, the amplitude ratio is reduced as a function of two parameters only, which are omega over omega n. Omega has, this is a useful ratio because omega can be either less than omega n or equal to omega n or greater than omega n. Okay, and as function of zeta as well, which is 2 zeta omega over omega n. So we reduces the parameters into 2 only. That will be easy to study. And of course, changing K or changing C or changing M is going to change omega n and zeta, because omega n is square root of K over M. And zeta is C over CC, which is function of M and K as well. And C. So changing M, K, or C is going to change omega n and change zeta, or change omega over omega n. Regarding F naught is X is directly proportional with F naught. As you increase F naught, you increase this X. This is direct proportion. So that is obvious that X is directly proportional with F naught. If F naught is large, as you increase F naught, X will increase. Okay, because if you take F naught here, as you can see, it is on the denominator and without any, this is not under square root or square or whatever. So it is directly proportional with F naught. The same thing with the phase, introducing dividing by K and multiplying by K, we get tan phi equal to 2 zeta omega over omega n divided by 1 minus omega over omega n squared. So we reduces the amplitude and the phase in terms of two parameters only, which are the frequency ratio, omega over omega n, and the damping factor, zeta, or damping ratio, zeta. So now you can plot the particular solution, not the total solution. This is the particular solution. And study the ranges we have. Okay, this graph shows the amplitude ratio, which is kx over f naught, versus the frequency ratio omega over omega n for a given zeta. Here some zeta or some curves of some values of zeta. Zeta equal to 0, zeta equal to 0.05, and zeta equal to 0.1, and so on. Only some of them are shown here because you cannot show all, because there's infinite number of zetas. Okay, so these samples are shown here. Zeta equal to 1. Okay, zeta equal to 0.5, 0.35, 0.375, 0.25, 0.15, and so on. And also the phase is plotted versus the frequency ratio for different values of zeta. Now we'll see that Now, the mass is subjected to a force under a given frequency. But this will tell you which range is more safe that lead to small amplitude and which range is unsafe that lead to large amplitude. Okay, so you can see there are three ranges as we did before, that omega over omega n can be less than 1 or equal to 1 or greater than 1. Now, if it is very much smaller than 1, this symbol means very much smaller. Which is very close to 0, somewhere here. Okay, there are all curves almost the same in this range. And the phase near 0 is almost 0. Okay, so the polygon that we used in solving the differential equation will have that this is a typical polygon of forces, that the phase will be very small, and then which means that inertia force is small and the damper force also small. The burden, the load is carried by the spring in this case, if omega over omega n very much less than 1. Okay. If omega over omega n equal to 1, you will have a division by 0 in the phase. Okay, so 2 zeta omega over omega n over 0, which is equal to infinity at omega over omega n. And this is the case when the phase is 90 degrees. So regardless of the value of zeta, if you have omega over omega n equal to 1, the phase equal to 90 for all zeta. So as you can see here, this is 90 for all curves. The phase is 90 degrees for all phases, for all damping. And the polygon would reduces to parallelogram. If not, it's parallel to the damper force. The spring force is parallel to the inertia force. And the inertia force or the spring force, the spring itself carries the inertia of the mass. It is not carrying F naught. The damper is carrying F naught. And this is the resonance case. And this is what happens. Imagine that you don't have, if C is equal to 0, then there is no force opposing F naught. And that means the amplitude would be infinity if C equal to 0. Okay, or damping is small. And as you can see, if damping is small and we are at resonance, this is the resonance case, the amplitude is affected by damping. If zeta is 0, this is outside the range and it might be infinity. And when zeta is 0.05, this is still outside this range. Zeta equal to 0.1 is even outside. Zeta equal to 0.15, we still see the peak, which is very high. That is the amplitude ratio, not the amplitude, this is the amplitude ratio. This is very high. And as you increase zeta, this peak or maximum, it drops. So it means that at resonance, the amplitude ratio is controlled by damping, not by the force, the spring force. Okay, so there is effect on the effect of damping is very clear here at resonance. And when you move to the third case, when omega over omega n very much greater than 1, very much, this is very much greater than 1, the phase will approach 180 degrees, and then this damper force and the spring force will be small, but the inertia force is large, and the inertia force is opposing the applied force. And the damping has no influence on the amplitude. as you can see from the graph of the amplitude ratio versus the frequency ratio for the range omega over omega n greater than 1 with like 3, 4, 5, 10. All curves are merging as one curve. The one with zeta equal to 0 and the one with zeta equal to 1 become one curve. So there is no effect of damping on the amplitude here. So this is why many machines, if working at this range, in this range, they don't need a damper. Okay, you don't need a damper here. But if the working condition is near resonance or at resonance, the only way, one way to control the amplitude ratio is by increasing the damping coefficient C or zeta in general. Okay, so we can observe some notes from the graph. The damping has large influence on the amplitude and phase angle in the frequency region near resonance, but damping on other regions has no influence. On near 0 or very much greater than 1, we have the amplitude. The damping has no influence on the amplitude. Okay, the maximum amplitude occurs at a frequency lower than the nature frequency. We have two things here. The peak, the amplitude ratio has a resonant amplitude. This is, for example, zeta equal to 0.375. This is called resonance amplitude, which means at omega over omega n equal to 1. And this is called peak amplitude, maximum. And the maximum occurs before resonance, just before resonance. But this can be, for zeta very small, the peak and the resonance amplitude are the same, because the effect of damping here is very small. Okay, so we will, okay, we'll finish this one. Okay, in summary, we can write the differential equation and its complete solution, including the transient term, as this is the differential equation, which was mx double dot plus cx dot plus kx equal to f naught sine omega t. If we divide by m, we get x double dot plus c over m, x dot plus k over m, x equal to f naught over m sine omega t. C over m is 2 zeta omega n, and k over m is omega n squared. So you can see that we can, we talked about this in chapter 2, that when you divide by m, then you make the coefficient of x dot is 2 zeta omega n, and the coefficient of x is omega n squared. The total solution consists of is the addition of the homogeneous plus particular. This is the particular solution. This is xp, and this is xh, and this is for zeta less than 1. Okay, because this is the underdamped solution. Okay, we will continue inshallah from this slide. Next time we will have an example as well. Any questions?
Doctor, I have a question about the assignment.
Okay.
Question 5, Doctor, I didn't understand ما فهمت الماسز، يعني الماسز شو اسمه نفس بعض هما ولا يعتبرون غير؟ الماس في A وماس في B وفي الماس مال بار، فهو كان ماس مال بار مكتوب M على 4، فهل هي الأم نفسها مال أم ال B وأم ال A؟
Question number
5.
Okay, I will make sharing so that you can see the question. Question number 5, you said, right? Okay, question number 5. Find the equivalent spring constant and equivalent mass of the system shown below with respect to x1. Okay, x1 is at A. Find data frequency. Assume that the bar or A or B is rigid with mass MB. Okay, and mass moment of inertia JO about 0.0. The spring attached to the mass at A has a mass MS, and the other springs are of negligible mass. Okay, and take MB equal to M over 4. We have M here. Okay, this is M, right? And the mass of the beam equal to the mass given here over 4.
اوكي بس كنت اتاكد بعد
أي.
الام اللي في نقطه بي هي نفسها نفس الام اللي في نقطه اي لا؟
اي نفس الشيء. سيم.
تمام.
اوكي. يلا بالتوفيق. طبعا قلت لكم ان في there will be makeup test on Sunday at 3 for those who were absent. If somebody wants to repeat the test, he's welcome, but I'm not going to mark his paper in details. So you get this, you get the full mark when you get the correct answer. You get 0 if you don't get the correct answer. But it's worth to try because I'm going to take the best.
تمام دكتور.
Yeah, awesome.